Assalamu alaikum. My name is Muhammad Haris, and today I have to explain this question. So let me share my screen. Okay, the question is basically some root to leaf numbers. You are given the root of a binary tree containing digits from 0 to 9 only. Each root to leaf path in the tree represents a number. For example, the root to leaf part 1 to 3 represents number 1 to 3. Return the total sum of all the root to leaf numbers. Test cases are generated so that the answer will fit in 32-bit integer. A leaf node is a node with no children. So, for example, let's take this example 1, 2, and 3. Uh, so what we have to return? We have to return the numbers in the nodes, and then we have to sum at the end. For example, if we traverse to 1 to 2, we will take 1 2 number. If we traverse from root to left node, we will take 1 2, and then we will traverse from 1 to 3, we will take 1 3, and then we will add 1 2 and 1 3 at the end, and return the sum as the output, right? Like in this case, sum is equal to 1 2 plus 1 3. In this case, 4 in this case 49510. We will traverse from 4 to left node. Then at the end we will get 495 from this traverse. Then we will traverse from 491, we will get 491. Then after that we will traverse 40, root to right node 40, and at the end we will return the sum of all the numbers which we get in the end, which will be in the list. So 495 plus 491 plus 40 will gives us 1026. So the constraints. Let's look at the constraints. The number of the nodes in the tree is in the range 1 to 1000. So the nodes in the tree will be from 1 to 1000. The node value should be greater than equal to 0 and less than equal to 9. And then depth of the tree will not exceed 10. So basically, uh, what I did is I basically uh, did a pre-ordered traversal in which we go from root to right, root to left node, then right, root to left node, and then right. Simple. I've used the DFS pattern depth DFS pattern, and I used the pre-order traversal to solve this question. So basically, what I did is in this case, what I did is I traversed through all the left node first, from root to left node first, and then add it in the list as a string. For example, first I get is 4, I take it as a string, then I add it in a list. This is I took an empty list, and I increment the numbers which I get as integers in the list. So first I take a 4 value, I change it to string and add it to the list. Then I take 9 number, take is convert it into a string and add it into a list. Then I take 5 number, likewise. Then when I get to the leaf node, what I did is I take this list of strings and convert into a simple string like 495. Likewise, I will get from 491 and list of integers and convert them into a simple integers like 491. And likewise for 40 into 40. Then these are integers. These are basically integers. They cannot be uh, uh, add into a consider it to be an integer sum. So then what we'll do is uh, we will convert these numbers into integers and then add them at the end. So 495 plus 491 plus 40 gives us uh, 1026. 1026. So basically, we take a list of integers, list of strings, then convert them into strings, then convert them into integers, and then add it into a it and return it to a our function. So let's go to the algorithm. So basically, um, basically define some function. Root node is given. We will check that if the binary tree is empty or not. Is it empty? It will return 0. Then we'll take a output variable. Then we take an output list in which we'll store a string of numbers in this list. Then what I did is I take create another function pre in which pre-order traversal will be taken. First condition is if the node left or node right is empty. For example, if we are the if we are in the fifth node, which is the leaf node, then what will it do? It will append the numbers, the strings. For example, so far is the empty string in this function, and node is a node, simple root node. So when we get to 5, this condition is for the leaf node. When we'll get to 5, it will um, it will append the strings in the list and then convert that list of strings into simple strings by using some simple using join function in this case. So uh, join function, by using join function, we convert a list of strings into simple strings. And then the next condition, if node left, for example, if we are in 4, we are going to node 9. If there's no another uh, uh, left node of the node, it will it will do is it will pass the node left number, which is 9 in this case, and then uh, convert that integer node value, which is 4, into a string. So basically, in this empty list, it will add 4 as a string, and then after that, uh, 9 to 5, we will get what we'll get is uh, we will pass 5 value in our function again. Basically, this is all recursion method. So basically, 5 is going to a function again, and 9 is adding to the list of strings. Then we will get is list of 4 and 9. Likewise, we at the end we'll get 5. So we'll get a list of strings will look like 495. Likewise, for node road right, it will get 49140. After that, so basically, this statement is basically passing the root node and empty string. So after that, at the end, what we'll get is 495, 491, and 40. To add these strings, we first have to convert them into integers, which I have done this in this statement, and then sum it. So 495 plus 491 plus 49 plus 40 will gives us the answer, which is 1096 ICS. So it will give the right answer. So let's check the if it 1026. Yes, it does gives the right answer. It will gives the right, yes, submitted as well. So basically the uh, time complexity of this code will be uh, the time complexity of this code will be big O of n, because of the fact that we are traversing for every node, and the space complexity uh, in this code in this function will be program will be dependent on the height O of h. So basically, time complexity will be O of n because of the fact that we are traversing from every node again and again, and the space complexity will be O of h, in which h is the height of the tree. If the tree height is greater, it will depend on space complexity. Space complexity will be greater. We'll have more space, and if height of the tree is smaller, space complexity will be smaller as according to. So yes, now let's jump to question number 2. So let's jump to question number 2. Let me share my screen. So basically, uh, the question is first find first and last position of elements in sorted array. Given an array of integer nums and sorted in non-decreasing order, find the starting and end position of the given target value. If the target is not found in the array, return the -1 and -1, comma -1. You must return an algorithm with O of log n, O of log of n, runtime complexity. Whenever we are talking about O of log n, we most probably are talking about the binary search or the binary search pattern. So example 1, let's look at example 1. Input nums is equal to 5, 7, 7, 8, 8, 10. Target is 8. So we have to return the index in which we found a target, like in this case is 3 and 4. There's no target in this array, so we return -1, comma -1, and there's no empty array, so we return -1 as well, -1. So um, as I told, when we are talking about log of n, we are most probably talking about the binary search. So basically, uh, I've used the binary search method. So let me annotate it. So for example, take this sample, 5, 7, 7, 8, 8, and 10. So basically, this is very binary search. It can be done by binary search, but there's a trick in this question. First, what will I do is I will search the number in this portion, which is left portion, and then I will search the portion in this portion. If our mate is this number, then we will do in this subarray. I will search the number in this subarray, and then I will search number in this subarray, and then what I do is I return the indexes of the number of indexes of where the number I found it. So that's how it can be done in binary search. So basically, first I will take a look at this subarray. What I found at the end is that I found that the third number is at the third index 8 number is found, and this subarray 4 index is found. We can also what we I can do we can also do it by simply iterating using the binary search method. But what I do what I get at the end is I will get 4 and 3, 4 and 3. But what they are asking it, they are asking in a uh, sorted pattern. So I can use a sorted function, built-in sorted function uh, in the question, but sorted built-in function has a time complexity of n log n. But in this question they are asking of log of n time complexity, so I can't use that sorted built-in function. So that's why I divided into two sub array, left and right. And then what I did is I find the number in one sub array, left side sub array, and then find the right sub array. So at the end, the time complexities remains same log of n. So let's jump into the question also. Let's take a look at constraints. And the array length should be greater than equal to 0 and less than equal to 10 to power 5. The numbers in the array should be greater than equal to 10 to power minus 10 to power 9 and less than equal to 10 to power 9. Nums in a non-decreasing array. So nums is a non-decreasing array. It means that it is sorted, and the target value which is given is should be greater than equal to minus 10 to power 9 and less than equal to 10 to power 9. So let's jump to the question. So basically, this statement is for the empty list. If the list is empty, we return simple -1 like in this case. After that, I take a variable start and end and declare to -1 -1, and then I take the length of the nums. Then what I do is I initiate. initialize the left and right pointer to 0 and the length of the array. Then what I do is, this is for the left binary search for left. So I iterate to this in this array and find a number in that subarray. So for example, if mid is 8 in this case, so, and if number is less than equal to target, number mid is equal to less than target, so my right comes from 10 to here. So my next new subarray is 5778, and then after that I will check again if nums is equal to target. It is not equal to target. If our new mid, which is 7 in this case, will equal to target, it is not equal to target, so my left will come here. So my new subarray is 7 and 8. Then it will check again until and unless my left pointer, which will become 8 at the end, is equal to target, and my left pointer is less than the length of the array, because it can go out of bound. So that's why I created that check. If it's less than the end, and it's equal to target, we'll simple initialize the left pointer to the start pointer, which is -1 at its start, but will become equal to 8. So my left pointer will be the index of that number, so it will return 3. So, and the second thing, second search is obviously also, as I told before, is the binary search for the right side. So likewise, I initialize the left right pointer 0, and while left resident mid will become 8 in this case, in this example. So I will take a look at this subarray right now. If nums mid less than equal to target, so my left le- left pointer will come from 5 to 8, from 5 to this 8 and 10. So my new subarray is 8, 10. And then what I check it for the uh, I I take a look at this condition. If my right pointer is -1 is equal to target, yes, target and should be initialized to r-1, and then return the start and end pointer. Also, the fact that I use this if loop is, it can come out of bound. So that's why I'm checking that if right -1 is equal to target, return it at the start. Initialize the end pointer with r-1. So at the end, I get return start comma end, which will gives the right answer. So yes, it is the right answer. Yes, it is also faster than 66%. So yes, the time complexity, as I told, will be log of n, because it's binary search. We have done 2 times the binary search, but it will remain time complexity. Binary search will be remain same. It will be log of n by time complexity, and the space complexity in this case will be um, I haven't used the another data structure or list, so it will remain constant O of n, because I'm already iterating to this list. I haven't created another list, so another data structure, so that's why it will remain constant O of 1. So yes, and the test cases in this example will be this, that if there's no number in the uh, no numbers in the array, if it is the empty list. So what we'll do is, that's why I've used this if loop for this edge case. It will gives -1 at the end. Let's check it again. If the list is empty and also target is 0, so what will it give? It will give -1 from -1 in this case. Yes. So yeah, that was my solution. Now let's go to question number 2. Question number 3. So yes, let's go to question number 3rd. Let me share my screen. So yes, the question method is binary tree right side view. Given the root of the binary tree, imagine yourself standing on the right side of it. Return the values of the nodes you can see ordered from top to bottom. So basically, what we have to return is we have to return 1, 3, and 4. For example, if we had 1, 3, 4, 5, and if we had also 7, so we at the end we should return 1, 3, 4, and 7 as well, because from the right side you can see 7 as well. It is not covered as 2 and 5. So we will at the end we will return 1, 3, 4, and 7. So that's what we have to return at the end. And if likewise in example through 2, we will return the root node and the third node because it comes at the right side, and if the root node is empty we return the empty node. And look at the let's look at the constraints. The number of the nodes in their tree is in the range 0 to 100, so the nodes will be length of the nodes will be 0 to 100, and the value within the node will be greater than equal to 100 and less than equal to 100, greater than equal to minus 100 and less than equal to 100. So yes, I performed this question, did this question by using the BFS pattern, breadth first search. So basically this can be done by DFS pattern as well, but BFS is quite easy. So first let me notate. So basically what I did is I usually take an queue which is taken in BFS pattern. So what I did is I firstly we will insert a one in queue, one first node which is root node in our queue, which is one in this case. So after that, what we do is we will pop that node and return and insert the childs of left and right child, which is 2 and 3 as well. Also that we will take a uh, result a very result list which in which we insert the results. So firstly, we will insert the root node because it's the root node. After that, what we do is we insert its child, which is left child and right child of 1, which is 2 and 3 in queue. After that, what we do is we pop that queue. We pop the leftmost number in queue, which is 2 in case. Before popping the leftmost number, which is 2, we will insert the left and right child of 2. Left child the value of null, right child is 5, so we'll insert 5. After that, we will pop the leftmost number, which is 3, and before popping it, we will insert its child, which is left and right, in which in this case it is left child is null, right child is 4, so we'll insert 4. Likewise, we are inserting in popping. We will also take a look and at the uh, result list. So basically, what we are doing is before popping the number 3. Okay. Before doing this, what we'll do is we will look at the rightmost number before popping 2 and popping 3. We will look at the rightmost number, which is 3. We will insert it. After that, we will likewise pop 2, inserts its child, then pop 3, inserts its child, then look at which is the rightmost number in this queue, which in this case is 4, so we'll insert 4 as well. So this will be the result list, and we'll return the list at the end. And after that, if 4 have no 5, if we will pop 5. If it has no child, like in this case it has no child, so we will not add any numbers in the queue, nodes in the queue. Likewise, 4 has no child, no will not add we will not add any nodes in the queue, so we'll come out of the loop, and give the result in the output result list. So let me clear all the drawings and let's look at the code. So yes, I declare a result list. Then what I do is I create a DQ. In Python, we create DQ. After that, while my DQ is not empty, take a right side variable and give it to none. Firstly, after that, I take length of the queue, which will be considered levels. How many levels for example, in the root node, we will have one level. Uh, in uh, in this row, we will have two levels. So the length will tell us how many levels are there. After that, for I in range and node q pop left, we will pop the left variable. But we know that we will have to, but what we have to do is we have to insert the child nodes before popping it. So in this loop, it is appending the child nodes in the DQ. For example, if node is not empty, right side should be node. If node is not empty, for example, in this case, node was not empty. So I insert 3 in the node, 3 in the result, 3, I will take right side as 3 and insert the node left, which is uh, uh, two childs and 3 childs. 2 left, yes, no left of 2, so we'll insert 5. 3 left, yes, no left of 3, so we'll insert 4. Likewise, if right side is not empty, append in the result variable, and after that we'll get the uh, result list, which will be 134 in this case. So it gives the right answer as well. Let me submit it. It's also submitted and it is faster than 86%, so it's quite efficient. So basically, the time complexity will be O of n, because of the fact that uh, every node to check that if it is rightmost in queue or not. So that's why it is O of n. And there's also for loop, which indicates that it should be O of n. And the space complexity will be um, O of n as well, because we have used DQ in this algorithm. So yes, that was my uh, algorithm. Uh, Thank you for watching. Allah Hafiz.